is an exercise. The drawing is this one. If I compute by hand, or if I go to a program in the computer and I plug this equation and I tell the computer, okay, can you give me the PQ such that P Q to the square equals this polynomial in P, the computer is going to give you this curve. Now, this curve looks smooth. I mean, it looks that it does not have problems like this. Here there is a singularity, and here it appears that if I am in a point of the curve, everything is nice and smooth. It is the case. But as I have told you, the topology of this curve is not the Euclidean one, because this is an object from algebraic geometry. So if I want to throw a small ball around this point, this set is not an open set in the Zariski topology, because open sets in Zariski topology should be everything but a finite number of points. The intersection of this small ball with the curve is not everything minus a finite number of points, because there is an infinity of points of the curve here. So even if it looks like you can apply methods from differential geometry or differential topology to this object, the topology is the Zariski one, it's not the Euclidean. So you cannot do that. So algebraic geometry from one hand is very powerful because you can put a topology for every field. So Zariski topology is defined for every field. So Zariski topology is extremely general. On the other hand, when you go to the real numbers or the complex numbers that we have done these examples today, Zariski topology is extremely big. The open sets are very big. So local arguments, as in differential geometry that I was accustomed, I have the naturality of applying differential geometry here, like local methods using Euclidean topology. I cannot do that for algebraic geometry. So this is a big problem, because I would like to consider a finite topology to study my algebraic objects. So this was a very interesting question in the last century. Can I define a nice topology of fields such that I can refine the topology of my algebraic varieties to study them as I did with the Euclidean topology? So, what is the problem? The problem is that Zariski topology is very coarse, or is not as fine as one would want. So the question is, can a topology on K which satisfies the following thing. A topology tau K such that the Zariski topology is contained in this new topology, and this topology gives me more local open sources, so that I can analyze my algebraic varieties with more precision. This was a very general question last century. If I can find topologies on fields such that I can handle algebraic varieties with more local arguments. So, just to finish, because I think that 2 hours is too much for this kind of material, if the field is the complex numbers, we already know the answer, right? There is a Euclidean topology. If C is K, if K is C, then the Zariski topology is contained in the Euclidean topology, and this topology I can do anything that I want from the differential point of view. But what happens if K is not C? For example, maybe the only other field that interests us is the real numbers, right? Maybe the other field of interest is I, but something similar happens for R. We have the clear topology for R. But what happens if the field is not C or R? For example, Q. And you may wonder, okay, why would I be interested in algebraic varieties over Q? So what is an algebraic variety over Q? An algebraic variety over Q is a set of solutions in some space of polynomials with coefficients in Q. And this screams number theory. Arithmetical geometry is a generalization of number theory in which you use algebraic geometry to attack questions from number theory. So it is relevant to study varieties over Q from a number theoretic perspective. So Q disappears in algebraic number theory. For example, in Diophantine equations. So, algebraic geometry is very important, it's very useful, it's very interesting. Because many problems from classical mathematics can be reformulated in terms of polynomials. Anyways, so the question is that, let me finish with the following theorem, which is the second theorem of today. And I will finish with this theorem. This is beautiful. Because it originates in geometry. You have objects that you want to study locally, that comes from algebra, that comes from number theory, that comes from solutions of systems of algebraic equations. Those are your objects. The topology is very big. It does not work. Can you refine the topology? The answer is yes. And there are two ways to do it. Either you use the Euclidean topology or you use a crude valuation. So the moral of the story is that crude valuations belong to algebra. And now they appear in topology. They appear in geometry. So, again, I want to show you the unity of all these branches. Crude valuations define good topologies of fields. That's the lesson for today. I think I will finish here. Thank you.